Okay, folks, it's time to start the next online lecture. Lecture number 16. This is Physics in the Time of Corona. Today, our plan is to discuss magnetization, as well as bound currents due to magnetization and the H field. So the picture that I want you to have in your mind is that a magnetic material is what I've drawn here on the left. A magnetic material is a collection of little current loops, where these are the current loops, and the current loops create magnetic moments. The little m is a magnetic moment, and the picture you should have in your mind is that in a material, the atoms, the electrons in the atoms create magnetic moments because, as we saw last time, if I have the ith electron in an atom, then that has a magnetic moment associated with it, which comes from both the orbital angular momentum, L, as well as the spin angular momentum, S. And there's a factor of 2 because of the G factor. That's that little G factor there. And so when I draw these little loops, you can just think that all the little loops in the material are these guys. Okay, so a very important concept, though, is, as you remember, is that we like to think of things in the macroscopic continuum limit. Macroscopic continuum limit, because when we talk about E&M, we don't like to have to worry about counting up all the atoms and keeping track of every little electron. There's just too many of them. And so we like to think in a macroscopic continuum model. And here we can think of the macroscopic magnetization, which is the continuum magnetization within a material. And this is equal to the sum of all the little dipoles in a small volume divided by that small volume. And that is at the location R. And this way we can define the magnetization at every point in R. It's equal to this. It's equal to basically, it's the magnetic dipole moment per volume in a material. And this should look very familiar to you because here the idea is exactly the same as what we did for electrostatics. And you know how much I like to point out the analogies between electrostatics and magnetostatics. So I'm going to remind you of that. In electrostatics, we define a constant, we defined a quantity called polarization, which was equal to the sum of all the electric dipole moments in a little volume of a material. And so we're about, and that was quite useful because then it allowed us to define other very useful quantities such as the bound charge, which is equal to negative of the gradient of the polarization, as well as the surface bound charge. That's the volume bound charge, and the surface bound charge is P dot N. And these are very useful quantities. And so basically what we're going to do now is we're just going to do the exact same damn thing like we always do. We just keep repeating ourselves. We're going to do the same thing for magnetostatics that we did in electrostatics. So we're gonna show that there's also bound currents in magnetostatics. So the strategy then that we're gonna follow is the same strategy that we followed before for electrostatics. What we're gonna do is we're gonna consider some material which has some well-defined magnetization within it, in the material, and then we're going to have some origin living in there, and we're going to ask ourselves, what is the magnetic field at this field point, R, due to this material? And so this location, R, is here. Pretty close. That's R. And then we're going to ask ourselves, what is the B field at that point R? Well, we know what to do. We can look at we know what to do. What we can do is our strategy will be to first find the vector potential A at the point R. And once we have A, then we know that B is equal to simply del cross A. And so to find A, we will use the multipole expansion that we derived in the last lecture. Let's use the multipole expansion. And so what that means then is that to find the B at this little point, field point, I can consider a little itty bitty tiny volume there, and let's consider the that there's some little tiny magnetic moment in that little tiny volume, and that little tiny volume is in the source. It's r prime, and that little tiny volume is then creating some vector potential at the field point, which is connected to the tiny volume by the vector r, cursive r. And so then we know then that from this little tiny dipole, then we know that that creates a little tiny vector potential at the field point. And that little tiny vector potential is equal to mu naught over 4 pi times dm cross cursive r hat over cursive r squared from the multipole expansion. And so now we know how to get the total A at that field point is we just have to integrate. The total A is equal to the integral of all the little guys, all the little dm's. But of course, we know that dm is equal to the magnetization of the material times d tau prime. And so that means then that this leads to then A, the vector potential at the field point R, is then equal to mu naught over 4 pi times the integral of m, the magnetization of my material at the field point R prime, d tau prime cross r hat, cursive r hat, divided by cursive r squared. And so, okay, so that's what we get, and this is following the same strategy that we did for electrostatics when we did the same derivation for the scalar potential V, but now we're doing it for magnetostatics for the vector potential A. So what we're going to do is we're going to show. What we want to do is we want to rewrite this, and we're going to rewrite it using some fancy math, and that will allow us to derive, we're going to rewrite this, and that's going to allow us to derive bound currents and bound volume currents and bound surface currents. And so that's what we're about to do. Let's do that. So now we're going to use some fancy math to rewrite this expression. And so we're going to expand it out. It's going to look more complicated, but then it'll get much simpler. And so and it's the same thing we did before for electrostatics. Okay, so here we go. Let's do some math. So we know that cursive R is equal to R minus R prime. And so that means then that if I have 1 over cursive R, and if I take the gradient of it, del prime, then that's going to be equal to negative del of 1 over cursive R, because of that negative sign. But that derivative is equal to R hat over R squared. And we've done this before. That should be a familiar trick to you. And so what we're going to do then is we're going to use this, and we're going to take this part of our integral, and we're going to notice that that part of our integral is the same as that. And so we're going to replace it with this. Ta-da, that little part. So we're going to rewrite the integral doing that. And so what we have then is, so what we have now is A of R is equal to mu naught over 4 pi times the integral of m of r prime over the source, but now it's going to be crossed del prime 1 over cursive r integrated over volume, over the source volume, d tau prime. Okay, so I've just done a little math, but now we're going to, we want to rewrite this using vector identities, using calculus vector identities. Now we're going to bring in the calculus vector identities, yay. We always are using them in this class. And so this is the one that we want to use today. So I'm going to derive it. Let's use this vector identity, but first we've got to derive it. This is the vector identity. Let's start this. If I take the curl of an arbitrary scalar product f times an arbitrary vector field A, then if I use a product rule leads this to be equal to f del cross A plus del f cross A, which, and then I can just rewrite that del cross A, and I can just reverse that minus A cross del f, and so then I can pull that to the other side, and that leads to this vector identity, which is A cross del f is equal to f del cross A minus del cross f A. Okay, that's just meant to be an arbitrary vector identity, and so then what we'll do is for A we'll plug in m, the magnetization, and for f we'll plug in 1 over cursive r, and we'll turn all the dels into del primes, which we can do. It's still a vector identity, and then that allows us to so you can see how this part is equal to what's inside this integral. And so now I'm going to expand this integral into two integrals using these two pieces. So that then tells us that the vector potential A of r, and I'm sorry I used A when I derived this vector potential. I used A, that's just meant to be arbitrary vector field. Okay, but now let's go back to the integral. A of r is mu naught over 4 pi. Now I'm going to plug those two pieces in, and now I get two integrals. They look more complicated, but they actually help us a lot. 1 over cursive r times del prime cross m of r prime d tau prime minus mu naught over 4 pi integral of del prime cross m at r prime over cursive r and d tau prime. Okay, so we've now turned our integral into two integrals, and what we can do now. Okay, so now to go forward, this one is fine, but this one here, we want to change. Now to change that one, we're gonna have to do more math. So we're gonna have to use this vector identity. And this is a lot of math, but it's worth it in the end. And so we're going to use this identity. And I'm not gonna derive this one in class, but this is a vector identity. So it's another vector identity, and this is the vector identity. I'm gonna derive this by analogy. Let's start with this let's just start with Stokes theorem. It's a generalized Stokes theorem. So Stokes theorem, you guys all know, it says that if I have the curl of a vector field, And if I integrate that over some area, a membrane, like the flux of that curl, then that is equal to the line integral of that vector field around the edge. So there's a dimensional reduction. I go from the integral over the membrane is equal to the integral over the edge. And so now I'm going to generalize that to one higher dimension, because now I'm going to say this, you can see how this went from two-dimensional area to one-dimensional line. So basically what I'm going to do is I'm going to generalize this, and so now I'm going to say that if I have the curl of an arbitrary vector field, but now I'm going to integrate it over a volume, then I will now assume that this is equal to the integral over the surface of that volume of n cross f over the surface dA. And this should make kind of sense, because look, this is, I'm going here from 3D, so I'm taking the derivative of the vector field and integrating it over 3D, and that's equal to the vector field itself over 2D, integrated over the boundary in 2D. So it should look kind of familiar. And even the directions of the vectors kind of make sense if you think about it. But I'm not going to derive it. So I'm just going to take this as a theorem. That's correct. But I do want to just say that I did have a postdoc give this lecture once, and he was so mad at me for not deriving this that he derived it on a Post-it note, and he gave it to me, and so now what I'll do is I will post the Post-it note. We'll post the Post-it note derivation. So I think I will give it to G1 and have him post it somehow on B course. Post-it note derivation on B course. So if you really want to know the derivation of this, you can look it up. You can look up the Post-it note that my postdoc made years ago, which I never threw out. Okay, but now let's take this, this vector identity, and we're going to apply it to this guy here, zoop, that guy, because see how I have del cross f d tau, and so now here I have del, and so I could just make this could just be del prime, of course, it doesn't matter, and so now I have del prime cross m over r, and so that is my f, and so now I'm going to rewrite that integral, and so using this vector identity, you see that I can rewrite that integral. And so now I'm gonna, so I'll write both integrals down now. So my a of r is equal to this guy up here. It's equal to mu naught over 4 pi integral of, I'm gonna write it like this. I'm gonna write it like this in a very useful way. Del prime cross m of r prime divided by cursive r d tau prime. Okay, that's the term that we already had, the one that I said was fine. But now I'm going to use this, I'm going to rewrite this one that I said we want to change using this vector identity over here. And so this one can be now rewritten as plus mu naught over 4 pi integral integral over mu naught over 4 pi integral of m of r cross n hat over cursive r dA prime. Okay, So you can see how and I just, the sign, I got the little negative sign, that negative sign, because I just reversed this order. This equals negative F cross N. So I just reversed the order of the cross product. I got rid of the negative sign. Okay, so this is what we wanted. And so this is the result. I'm going to put a big box around it. And here's the big box around it. And and this is very important. I want you to notice that this is it looks more complicated than what we started with, but it's actually quite beautiful, because basically what it's saying is it should remind you of the expression that we derived before for the vector potential of, if I have some distribution of current density J of R, then remember we derived that if I want to know the vector potential at some point R, then I can just take an integral. If I do our standard geometrical construction, and then I can just take a little volume here of J of R prime d tau prime, and I can write my vector potential as mu naught over 4 pi times the integral of the vector potential J of R prime d tau prime over cursive R. So that's sort of our structure for how we calculate the vector potential. And so now I want you to see how these guys have the same form. And that's very important to notice, because what that means then is that this big integral that I wrote, I can rewrite it now. Those two integrals above, I can rewrite them like this. I can say that A of R is equal to mu naught over 4 pi times the integral of this stuff on top, which I'm going to call now J sub B at R over cursive R d tau prime plus mu naught over 4 pi times the integral now of this stuff on top, which I'm going to call now K sub B of R, actually R prime, it's the source, dA prime over cursive R. And I want you to, and here these new quantities, J sub B is equal to del cross M of R, and K sub B at R is equal to M of R cross N hat. And so we've derived these two new quantities. I'll call this the volume bound current, and here this is called the surface bound current. Surface bound current. And the point is that these quantities up here, I'm going up to this top integral, up here you see this quantity del cross M, it plays the exact same role as a volume bound current. And this quantity here, M cross N, it plays the exact same role as a surface bound current. And you can just see from the structure of the integral. And that's the big thing we just derived. And this is very significant, because basically what it's saying, what we're saying is that if I have any material, if I have some material and I know the magnetization, then the magnetization is all these little current loops, and they might be all changing in funny ways. there might be more current loops in some regions and fewer current loops in other regions. But if I have some material that has some magnetization, and I want to know the vector potential or magnetic field from this material, then all I have to do is think about all the B fields, all the effect of the B field and the A field comes. I can think of it as coming from the volume bound current and the surface bound current. And that should be very familiar to you, because let's go back. I remember I was telling you, let's go back. Remember we derived the bound charge and the surface bound charge for electrostatics. Look, it even looks similar. The volume bound charge is del dot P, and the surface bound charge is P dot N for an electric polarization P. Now we've just derived the volume bound current J is not del dot M, it's del cross M. And the negative sign is gone, but that's a small thing. And then the surface bound current is M cross N. So it should look very familiar. So we can think of all the magnetic field behavior of this magnetic material is encoded in the volume bound current and the surface bound current, and that kind of makes sense because it sort of makes sense geometrically, because if I have some magnetization, then if I have a material and I have magnetization in it, all these little current loops, then it kind of makes sense that inside all the current, these are little current loops, but inside the current cancels. Current cancels. And you can see that because if I have two current loops next to each other, like that, you can see how here, one is going up, one is going down. They cancel. They cancel right there. And the only place where they don't cancel is at the current cancels in the bulk. But the only place it doesn't cancel is at the edge. So it's finite at edge. So it makes sense that all these currents would cancel in the bulk, but I could still get some current at the edge. So that current at the edge that I'm drawing so poorly right now, that current is my surface current, K sub B. And in the volume, the current cancels in the bulk, but that's only if I have a constant M. If the M is changing in the bulk, then it makes sense that I could have finite. Then it makes sense I could have still some current in the bulk. And what we know is that if I look in the bulk, so now I'm just doing this. This is just hand waving, but I just want you to get an intuitive feel for it. In the bulk, you remember I have these current loops, and that's the current, right? And then they give rise to a magnetic moment. Now remember that if I look at the magnetic field created by that current loop, you'll notice that the magnetic field, the induced magnetic field, is in the same direction. It's parallel to M. So these M's, so the B induced by the current loop is pointing in the same direction as the M. It's very closely related to it. And so we can think that the B field in the bulk is proportional to the magnetization in the bulk. And so what that means then is we know that del cross B is equal to mu naught J. And so then but if we know that if the M and B are proportional to each other, then we can see then that del cross M, I replace B with the M, then that is equal to a J. In this case, it's the bound J. So I just want you to see, but this is by analogy because the B and the M. So if del cross B equals mu naught J, then it makes sense that del cross M should equal a J. This is just a hand-waving argument just so you can help to remember it. I want you to sort of see intuitively and physically that this makes sense. These currents are real. The bound current and the bulk current are real things. And so, okay, so that's how we think of that. And so now what we're going to do is let's do an example. Okay, so let's do an example. And for this example, let's consider a sphere with constant magnetization inside of it. And then let's ask ourselves, then what's B? Far away. At some faraway point. Okay, so let's just take a look at this. So let's draw it. Here's a sphere. And now I have some magnetization, constant magnetization everywhere. The magnetization is, let's say, and let's pick it to point in Z. So that's the magnetization. M equals, let's just call it mz hat, okay? So it's a constant magnetization in the sphere. And then we want to know what's the B field out here. So let's pick some point out here, R, and we want to know what's the B field out here. B of R equals what? Now, normally what we have learned to do is we would do a multipole expansion and we would integrate we'd look at all the dipoles inside this volume and calculate the vector potential at this point and add them all up and find out the total vector potential at this point, and then we would do B equals del cross A. But let's not do that. Let's use our newfound knowledge and let's realize that at every point let's ask ourselves instead, let's use this new idea. Let's ask ourselves, what's J sub B? What's the bound volume current? And what's the surface bound current for this situation? So the volume bound current is del cross M, but we see M is constant, so the bound current is 0. There's no interior bulk bound currents in this problem because the magnetization is constant, and del cross a constant, the curl of a constant is 0. Okay, but what about surface? So the surface currents, the surface bound current is going to be M cross N at the surface, where N is a unit normal to the surface, a unit vector normal to the surface. And so let's figure out what that is. So let's pick some location, some arbitrary location. I'll call that, say, R prime. And we see that at this point, N is pointing like this, N hat, and M is pointing like that. That's M. And this, let's draw our axis here. This angle is theta in spherical coordinates. And so I see that this angle is also theta. And so I see that M cross N in this case then is for these two little vectors here, it's pretty easy. M cross N is equal to the length of M times the length of N times sine theta between them. And did I say theta? Not phi. Sine theta. And the direction, if we use right-hand rule, M cross N, then you see that the direction is going to be in that direction into the board at that point, and that direction, of course, is phi hat. So that means that the bound current density on the surface is equal to M sine theta phi hat. So that is the current. So I can think of now that this sphere of magnetization, I can think of it now as a sphere of current. And now I can ask myself, well, what's the B field arising from that sphere of current? So now I can just use the B field is equal to, I can use the Biot-Savart law, because I know that B of R is just equal to mu naught 4 pi. The definition of the B field is equal to, and then I can just have here K dA cross R hat divided by R squared, because that's the Biot-Savart law. Biot-Savart law. And then here I'm using the same idea. Remember it was like IDL is equal to J d tau, which is equal to K dA. So it's the same kind of thing as before. And so all I got to do is now I got to do this integral. So now what I have is this. Now I have converted the problem to now a sphere of current. I went from a sphere of magnetization now to a sphere of current. And now I only have to worry about, if I want to figure out the B field at this point B, I now have to figure out the contributions from the surface current. And I've converted the problem into a new problem where now I have, at this point, I have a current which is K is equal to M sine theta phi hat. And now it's a new problem, and this problem is easier. So it's an easier problem. But I'm not going to solve it. That's as far as I'm going to go. And then you can finish it. I think it might be a homework problem. But I just wanted to set it up just so you can get a sense. So that's how we use the bound current. Okay, so now let's move on, and let's talk about magnetic fields in magnetically polarizable matter. So what we did just there is we defined what we did before is we defined the bound current and the volume bound current and the surface bound current. So that's what we just did. But now what we're going to do, we'll talk about something new. Now we're going to talk about magnetic fields in matter. And this will lead us to the H field. A new field for us. Yay, a new field. We love new fields. Okay, and so the idea is, so why do we want the H field? Why do we care about this? Why are we inventing a new field? Although we haven't invented it yet, but we're about to. This is why. Let's consider this very important problem. Suppose I have a solenoid. Now, remember, for electrostatics, I always drew capacitors, because for electrostatics, the most important device is a capacitor, two parallel plates that make an electric field, and we're always sticking things into the capacitor. But for magnetic material, what we do is we have a solenoid. That's the most important thing. And the solenoid creates a B field. And solenoids always create constant B fields inside. And you learned that in some lower division course that you took a long time ago. So there's a B field in the solenoid. This is I'll call this some current. I'll call it, since it's not bound current, I'll call that free current. That's free current is the electrical current that flows through wires. That's different from this bound current that comes from magnetization that we were just talking about. Okay, so I have some current through that wire. I create a B field, and so now the idea is, let's put some material inside of there. And this material has some magnetization, M. The material magnetizes in that B field. And this magnetic material will, of course, have some bound currents, right? There'll be some bound currents in that material, depending on the details of the magnetization. Okay, and so the question then becomes, this is the question, the question I want to answer is, what is the B field? What is the B field? In the material, out of the material? What is the B field all around there? And that's the question we want to answer. What is the B field, say, in the solenoid? In the solenoid. Or out of it, it doesn't matter. But what is the B field? And so that's actually a hard question to answer. And I want you to remember why. Because we did this exact same problem before. Remember? And I always, you know how I always like to bring in the electrostatics. And I want you to remember how we did this exact same derivation before. We're going to do it again. But for electrostatics, what we did, remember, for electrostatics, we had a capacitor, and we created a battery, and we said, suppose we have a capacitor, and we stick some material in the capacitor, and the material in the capacitor creates some electric field, and then we have some material in the capacitor, which is a dielectric, and that material polarizes, polarization P, and it polarizes. Remember, the polarization goes in the same direction as the E field, and to do this, to solve this problem, and remember we said, what is E? What is the electric field in the capacitor? And that was really hard because the problem was that the electric field changed the electric polarization, but then the electric polarization changed the electric field, which then changed the polarization, and it was like a weird self-consistent loop, so it was hard to solve. But what we did was we looked at all the charge density, and we remembered that we had del dot E is equal to the total charge density over epsilon naught, and then we remembered that we had the polarization vector, divergence of the polarization vector gave us the bound charge density, and then this allowed us then to derive a new field, the D field, D as in dog, and the divergence in the D field came from the free charge. And this turned out to be very useful for figuring out how to do everything. And we defined this D, and this D field, remember, D was epsilon naught E plus P. And this D field was very helpful. It was an intermediate step to define this D field, helped us to solve this problem, because we used this relationship is very, very useful. And the insight is that total charge creates divergence in the electric field, bound charge creates divergence in the polarization, and free charge creates divergence in the D field. So it's sort of like charge creates divergence in our various electric fields. And the electric fields I'll call here, E, D, and P. I'm sort of defining them, calling them all electric fields because they're all sort of the similar kinds of things. Okay, that's what we did before, and I'm sorry for that, that little aside, but I think it's quite useful because now we're just going to do this whole thing again, but now we're going to do it for magnetostatics. And so so now we have the same problem. I'm going to sort of put a circle on this. Let's sort of box this off on the side. And so now what's happening is that we have the same problem, because when we're asking now what is the B field in the solenoid, the problem is that the B field is going to cause the magnetization to change in the magnetic material, because remember, magnetic material just has a bunch of little current loops and they're all going to align in the B field. And so, oh God, I got to take this call. Hello?
Hi, Mike, this is Jennifer. I'm calling out on Borrow and Son Plumbing and Heating.
Yeah?
Hi, I was just calling. We have you on the schedule for tomorrow to start the install.
Okay,
I just wanted to confirm everything with you.
Yeah, I confirm it. Please email me. I can't talk right now in the middle of this important meeting. I gotta go. Okay,
Oh,
bye bye.
bye.
Sorry, I don't know how to stop this recording. I don't want to lose this recording. Sorry for doing that, but I don't know how to stop the recording. I haven't figured that out. Sorry for that. Okay, so we have the B field, but that might have been an emergency, so I had to take it. So we have the B field, which which changes the magnetization, and the magnetization changes the B field, and then the B field will change the magnetization, and it just keeps going around and around. So we have that same current loop. So it's really hard to figure out what the B field is in the solenoid, because once I turn on the pass current through the solenoid, it changes the B field. I get the normal B field like you have derived in lower division class, but that then changes the magnetization, but the magnetization will then change the B field inside the solenoid, which then changes the magnetization, etc. So it becomes really hard to figure out what to do. So what we're going to do to solve this, the way that we get past this and solve it, is to go and do the same thing where we're going to analyze it using currents. So we'll analyze not through the fields, but through the currents. Whereas same thing here. See here, for electrostatics, we analyzed it through the charge density there. But now we're going to analyze this one through the currents. Not the charge density, but the currents, the current density. Analyzed through currents. And so what we're going to remember is that we have, we're going to remember that J total, the total current in any system, is equal to the free current, which is just the current going through the wires, like I drew here, plus the bound currents, which is the material, which is, so this is basically, the free currents is in the wires, like the circuit, and the bound current is always what we get from the material, material. So, so what we do then is we can now do a very simple thing. We know then that we know that we'll just use Ampere's law. We know that del cross B is equal to mu naught J. And so if I have the total B field, then that's the total current. And so I can say that del cross B is equal to mu naught J total, which is equal to mu naught J free plus mu naught J bound. But J bound is equal to, I'll write it, J bound is equal to, we know it's equal to del cross M, because that's the definition of the bound current. It's the curl of the magnetization. So what I can do then is I can take this and I can bring it back all the way back. And so now I can have, I'm going to bring it all the way back, and I'm going to have, well, first I'll divide everything by mu naught. And then I'll bring this one back. And then what I get is del cross 1 over mu naught times B minus M is equal to J free. See, because I brought that del cross M and then I just rewrote it like this. And so this is really cute, because now we see that the J free, here's the thing, this is the way we think about it. It's like, if we have J total causes curl in B, and then we see that, we know that J bound causes curl in M, because that's the definition of J bound. But now we see that J free causes curl in something else. J free causes curl in this weird quantity, 1 over mu naught B minus M. We're going to call that H. And so we're going to call that the H field. And H is equal to 1 over mu naught B minus M. This is our new field, H. And the reason we invented it is because current causes curl. Current causes curl. And so the total current causes curl in B. The bound current causes curl in M. And the free current causes curl in H. That's the important insight. And I want you to see how it's exactly the same as the electrostatics case, where total charge density causes divergence, because charge causes divergence. And so total charge density causes divergence in E, bound charge density causes divergence in P, free charge density causes divergence in D. Same thing here. All right? Total current density causes curl in B, bound current density causes curl in M, free current density causes curl in H. That's the new insight. Okay, and so then we see we have this new equation, which is that del cross H equals J free. It's from up there, and so this is our new equation with using our new field that we've just defined. And so let's see how let's just sort of think about this. Let's apply it to a couple of situations, and because now we have this weird new field. But I think before before we do that, let's just say a few intuitive words about the H field. First, when you think about H, you should think of it sort of like the applied field. It's the applied field. And then M is sort of the material response, and then B you can think of as the total field. That's sort of the way to think about it. Although that's just that's a sort of an intuitive way of thinking about it. Really, it's just the equations, it's really the equations that are correct, but this is sort of the intuitive way to think about it. And that will help you if you think about it like that. Also, I should add that you will also notice something. If you look at the electrostatics versus the magnetostatics, in the electrostatics, we have this. We had D is equal to epsilon naught E plus P, which meant then that we have E is equal to 1 over epsilon naught D minus 1 over epsilon naught P. Whereas for magnetostatics, we have H is equal to 1 over mu naught B minus M, and so we end up with B is equal to mu naught H plus mu naught M. And these formulas are a little different, the structure of them, and so it can be confusing when you first look at it. Because here you can see for the E field, I see that there's a negative sign here, whereas for the B field, I have a positive sign. And the reason is because the reason is because if I have a material, then remember that if I put an electric field on E, the polarization goes in the direction of the E field. But an electric dipole is a plus on top and a minus on the bottom, and so the induced electric field is in the opposite direction. the induced electric field opposes the applied field. So I should say it opposes the D field. So that because the applied field is like the D field, whereas for the magnetic case, you see if I have the same thing, I have a B field, and I have a magnetic material, and it magnetizes, and the magnetization is in the same direction as the B field, but now the magnetization is made of little loops, and the little loops create a B field, but now the B field is parallel to the applied B field. So the way to think about it is that the applied field here is the D field, and here the applied field is the H field. So we have the applied field, which magnetizes the material, but now the B field, the induced B field, is parallel to H. And so that's why in one case we have a positive sign, whereas in the other case we have a negative sign. So I just want you to notice that, because the magnetization increases the overall B field, whereas here the electric polarization decreases the overall electric field. Okay, so let's see. What we can do is we can. So now let's just look at some examples of how we use these new formulas. For example, if I have a situation like this, now I have a solenoid. Let's consider an example. I have a solenoid and I have a current flowing through it, and I could ask you, I could say I have n turns per length, and I could ask you, I could then ask you a question. I could say, what's the B field inside? What's the magnetization inside? What's the H field inside? And so you can the way to think about it is, you look at this and you first say, well, is there any free current? And if there's free current, so a nice way to do it is you say, if there's free current, then you immediately go to H. If free current, then we go right to the H field, because we know that del cross J free is equal to, I'm sorry, I've screwed that up, because we know that del cross H is equal to J free. And so and from this, we then know that the integral of H dot dl is equal to the free current enclosed, I free enclosed. And so that's just the integral form of Ampere's law, which comes directly from this. And so now we can then do an Amperian loop, and then we know that here we expect to have a B field pointing in this direction. We expect to have a B field pointing in this direction, B, and so then we can, or I should say in this case, H, and so we expect to have an H field pointing in that direction. So then we have, from our Amperian loop, if this length is L, we have H L is equal to L times N from this formula here. And so then we just see that H, and it's HLN times I. So, because that's the current enclosed, and so we have H is equal to NI. All right, so that's the H field inside. And so now the B field, so now let's see the magnetization. That's the easy one. So M is 0 because there's no material. M equals 0 because there's no material. Because M is the magnetization of a material. And so then it's easy to get B, because we know that B is equal to mu naught H plus mu naught M. And so if that's 0, then we have B equals mu naught H, and we have B is equal to mu naught Ni, which is a familiar formula that you've derived before for solenoids. But I just wanted you to see it in this case. And one of the things that we see here is that the B, in this case, the B and the H are kind of the same because there's no magnetization from the material. But let's consider another example. And so in another example, we would have, let's consider this. Let's consider a magnetized cylinder. I have a magnetized cylinder. Magnetized cylinder. And the magnetized cylinder has the magnetization is going up in the z direction. And then we can ask ourselves, now we can ask ourselves the same thing. What is B, H, M? And so this, in this case, the M is easy. So we know that M is just going to be M z hat because it's given in the problem. The magnetization is constant this is a magnetized cylinder. But then we can ask, but the other ones are not so easy. So what we can do is we can say, well, let's see. So in this case, we can there's no free current. So there's no free current. So let's just go right to B but there is no free current, but there is bound current. Bound current does not equal 0. And so we see J sub B, the volume bound current, is equal to del cross M. Now the volume bound current is equal to 0 because it's constant, and so the curl is 0, but the surface bound current is equal to M cross N hat. And we can see then that if we look at this construction, the N hat is pointing in that direction, and so M cross N hat is pointing in this direction. That's in the phi hat direction. So KB equals M cross N hat is simply equal to M times phi hat. So we see that we do have a bound surface charge, surface current density. And so this bound current density leads to a B field. And so because the B field, it just comes from all the current, and this is the only current in the problem. And so we can then do the same trick. We will do our Amperian loop. This is of length L, and we know that the integral of B dot dl is equal to mu naught I enclosed, and this then leads to B times L is equal to K times L. And so that then tells us that I got to put the mu naught in front, mu naught I. And so then we see then that B is equal to mu naught K. So we got the B. And it's and we see but it's pointing in this direction, and then we can, but it's pointing in the B is, let's see, mu naught K, but now it's in the z hat direction, and we can then find the H, because we see that H is equal to and K we know is equal to, of course, the bound current is just M, and so B is equal to mu naught M. And now the H is equal to, where's the form for H? 1 over mu naught B minus M. So H is equal to 1 over mu naught B minus m. And so when we plug it in, we get 1 over mu naught times mu naught m minus m is equal to m minus m is equal to 0. And so we see that here, in this case, the h is equal to 0. And that kind of makes sense because there's no applied field. So in the first case, there was an applied field, but in this case, there's no applied field. Okay, so that just gives you a little sense of how to manipulate these formulas. But now what I want to do, the last thing I want to do is I want to talk about boundary conditions, because now that we have H, it's important to think about what are the boundary conditions. And this will be the last thing that we do, boundary conditions, and then we'll be done. So here, let's talk about the boundary conditions. So these are the boundary conditions on H, because you know how whenever we come up with a new field, it's important to always figure out what are the boundary conditions. And so what we have then is we have the definition of H, which is 1 over mu naught B minus M. But we can also write B in terms of H. B equals mu naught H plus M. And the reason I'm doing that is because we already know the boundary conditions for B. We already did that. But let's just remember for B. Let's just remember the boundary conditions for B. Remember B, C's for B. And then we're going to find the ones for H just like that, just like that we did before. So for B, remember the idea is that we have some membranes subdividing two areas. We'll call this area 1, and this is area 2. And then we have some B field, which might change sign or change direction. We have some funky B field. And to make this a very general problem, we just say, let's assume that on that membrane, on the interface, we can, to make it most general, we can say, suppose there's some current density flowing through that interface. That's the current density coming out of the board. And then I have to define a normal vector too, to the interface n hat. So for this type of geometry, we remember we did it by figuring out. We did an Amperian loop. Remember, and we also did the pillbox construction. And we said that these both are of some height h, but we took the limit as h goes to 0. And then we used del dot b equals 0, and from that we then have we know that the integral b dot dA equals 0, and so we did that in the pillbox, and that's the pillbox there, pillbox. And so we saw that, and so that then leads us directly to B2 perp minus B1 perp equals 0. All right, so we got that. And then for the other one, and remember one of the whole points, an important point is that we had to write B is equal to B perp plus B parallel, where this is the perpendicular component to the interface and the parallel component to the interface. So we see that the perpendicular component is always 0, but then to find the parallel component, continuity, we used del cross B is equal to mu naught J total. And so then we did the Amperian loop, and from the loop, then this led us to B2 parallel minus be one parallel. Well, actually, let's get rid of those. Is equal to mu naught k. All right, so that was easy to derive using the loop. But then when we look hard at the directions, we see that turning this into a vector equation, it's actually mu naught k cross n hat. And you can get that just by looking at the directions. So this is what we did last time. That's just review. That is just review. But now we're going to do the same thing for h. And so for h, what we see is that we're going to get the boundary conditions. You always get the boundary conditions from the divergence and the curl of a vector field. And so now I got to look at the divergence and curl. So for del dot for del dot h, we see that del dot h is equal to 1 over mu naught del cross b, 1 over mu naught del cross, del dot b minus del dot m. But of course del dot b is 0, and so we see that del dot h is equal to minus del dot m. So the H field does have could have divergence if there's divergence in the magnetization. But now the curl, del cross H, we know of course already, is just J free. That's what that was the starting point. That's the definition of the H field, really. And so now we can do the same thing because we have our region of space divided into two halves. We can put a current through it, but now the current is K free because and then we have the n hat because we're talking about a free current there, and so then what we have is so this is the most general case, but now we have two materials where we'll have now on this side we'll have magnetization 1, and on this side we'll have magnetization 2. And so now we could have some H field here, H1, and H field 2, and we're going to break the H into the H perpendicular plus parallel, like we did before. And so now we're going to do the same thing. We're going to do the Amperian loop, and then we're going to also do the pillbox. And they have some length h, and we're going to take the limit as h goes to 0. And we'll just do the same thing. So let's start with the normal case. Let's do the h perpendicular case. And so this one comes from the pillbox analysis, pillbox. And so from the pillbox analysis, we see that if we do this, we see that the integral of h dot dA is just going to be exactly the same as the integral of negative m dot dA from this divergence, from these expressions. And so then when we do this on the pillbox, we're going to get h2 perp minus h1 perp. That's kind of messed up. We're going to get h minus h1 perp times a is equal to negative m2 perp minus m1 perp times a of the pillbox, so the a's cancel, and we see that the change in the perpendicular component of h is exactly equal to the change, the opposite of the change in the perpendicular component of the magnetization. Okay, so this is the boundary condition on the perpendicular component of H, and I will be honest with you, this is not a very useful one. This perpendicular component of H is not useful, because it depends on the magnetization. So you don't see this used much, so that's not useful, not too useful. But the one that is useful is the parallel one, the parallel component. Because now for the parallel component, we do the same. Now we do the loop, and we see that when we do the Amperian loop, we're going to get H2 parallel minus H1 parallel times this loop, and this is the loop right here. The width of that loop is L, so if you do that loop, you're going to get times L, and that's going to be equal to K times L, and then the L's cancel, and you get H2 parallel, and that's K free, because the current through there is the free current, because we're doing, remember, we're doing this comes from the integral of H dot dl is always equal to the free current enclosed. There's no bound current, so we can ignore the bound current for this one. We don't have to worry about the magnetization. And so this is H2 parallel minus H1 parallel is equal to K free. And if you think hard about all the directions, then you realize that I have to write it like this: K free cross n hat. And so that's the boundary condition on H. And so this one is very useful. Okay, folks, that is where I'm gonna stop.